again, and we continue. So one thing I forgot to say is that this normal property is, well, quite obviously satisfied when all these effects, there are projections, which, if you remember, was the case if the observables are given by self-adjoint operators. And in general, such POVMs that have only projections as effects, they're called sharp. And they have this property. And position is an example. So this, this is also a sharp POVM, even though it doesn't come from a self-adjoint operator, but these operators of multiplication, they are projectors. So, well, they square to 1. If you multiply by a characteristic function, you can do it again and nothing happens. They're self-adjoint and blah blah. Okay. Another example is given by coherent states. So a coherent state is given by a cyclic vector. So it's a vector in a Hilbert space such that this orbit, this set, is dense in the Hilbert space. And this is called a system of coherent states, and this is used as a definition in some, or as an example of a quantum reference frame in other approaches as well. And but one needs to be careful, because often more general definitions of coherent state systems are given when these cats, they're not necessarily like properly states on in a vector space, but they're understood in distributional sense. So one needs to be careful, but if this is an actual vector, a cyclic vector, then this is a coherent state system I want to care about. And if this system satisfies some property, they resolve the identity in the sense that you can define this integral. So it's an integral with a group. This is the Haar measure, so I didn't tell you this, but any locally compact group, so any group that we care about here, has this specific left invariant Haar measure, and that's the one here. So we can take an integral over these projection operators, and well, if some conditions are satisfied, but this is non-empty, so there are such things, then this integrates to the identity operator. And if this is the case, which is assumed in, for example, in the perspective neutral approach, when this is the sort of frame that's been considered, then this kind of coherent state system, it defines a POVM by this formula. So that one can check that because these states are being just rotations of the single one, this gives rise to the covariant property of a POVM, and this integrability condition makes sure that everything is finite.
Lambda is a real number.
Lambda is a real number, yes.
So for these, okay. So since it is normalized by this 1 by lambda, so their norm actually comes up to be 1.
Yeah. But one needs to make sure that lambda is finite.
Mm-hmm.
Otherwise it breaks. So often one just see group elements being written in the cats. So people just write something like
like this, unfortunately.
Huh?
Yeah, this doesn't work.
It doesn't work.
Or you can.
It was working last time.
Wait, there was some way to do it right. Was the notation thing? Yeah, it was that.
Okay.
Yeah. Yeah, I can close that, I think.
This or
yeah, I think it was this.
Yeah, it's fine.
Yeah, no, just right.
no, that's right. Okay. So what I wanted to say is that, for example, when people when one is concerned with like a frame for position, then you can see something like this being written with x being a real number, and well, in general, it can be a group element, and then an action is usually considered like the regular representation. So an action on these things is just given like this. So this is very nice, but it is only well defined if the group is countable. Because we want this different vectors to be orthogonal, this is a notion of an ideal frame. That I'm gonna say what I think ideal frames should be, but very often when you read the literature, these are the conditions that are being spelled out. But it is important, I think, to understand that in the case of real numbers or any continuous group, it's not even about compactness. This doesn't make sense, because if it would, then we would have these cats. They would define another basis of a vector space, because we assume they're orthogonal. But we know that in our Hilbert space it's separable. Then we only have a countable basis. Okay, what happens?
That you're,
We can only have a countable basis. So if the group is not countable, it's not discrete, then this cannot make sense. So there are different ways to deal with this. For me, an ideal frame would be just a sharp POVM. But you can also try to think about these elements as not being vectors in the Hilbert space like we assume here, but being distribution on states. But I'm not going there. It's just a side comment, so to say. Another comment is that if we want such a POVM to be sharp, so exactly what I just said, well, so these projections, then G can be, G has to be discrete for this to happen. Right. So yes, it is useful to distinguish types of frames by just saying what kind of properties these POVMs satisfy. First one is the principal, which we already sort of assumed. So the sample space of the POVM is just a group. Otherwise, it could be a homogeneous space or something even more general. The frame, so I use R as to denote the frame from the reference. The frame is sharp if this POVM is sharp, so all the effects are just projections. And a frame is ideal if it's principal and sharp. And it turns out that when I fix my system and the representation of the group, there is only one sharp covariant POVM. This is unique. And an example is this, again, this position observable that we've seen. So if I take the regular representation, there's only one POVM that is covariant and sharp. So the ideal frames are unique, one could say. And you can see that this definition is I think it's just better than the one that's given with these coherent states, because we don't have to go out of the Hilbert space setting and talk about distributions, and we don't need to assume the countability of the group. We never care about the actual vectors or coherent states. We just assume that the effects of a chosen observable, they are projections. Okay. The frame is localizable if the POVM is localizable. There are some. Well, it's complete. Well, there can be a subgroup that fixes the effects of the frame, and if this is the case, then the frame is incomplete. Otherwise, it's complete. We're not going to use this. And then a frame is a coherent state frame if it is constructed from a coherent state system, as I showed. Does this definitions make sense? I think the ideal frame and the localizable frame are they're really important. And maybe one more thing. So there's this notion of dilation. So if you have a POVM, you can construct another one on a different Hilbert space that is equivalent in a precise sense, but is sharp. So, some people say that this is, therefore it's enough to only speak about sharp POVMs. I don't necessarily agree, but it's good to know that that's the case, and it also works when you keep the covariance property of a POVM. So if you have a covariant POVM that's not sharp, you can also dilate it to have another one that is sharp and covariant still.
Oh, it is always like.
It's always possible to construct one.
So
Yes.
is sharpness somehow related to purification somehow, or since they're talking about dilation, or is this just like it's similar and the name's the same, but it's
No, I think it is related, but I don't know how. I'll take a look and I'll get back to you on Thursday. I think they should be related, but I don't have it on the top of my head. I don't see this now.
So you could also ask for this covariance at the level of unsharp such.
Yeah, so I don't assume sharpness from the outset. I take a POVM that is covariant.
But that may not be necessary. Like maybe at the sharp level they have this covariance, but maybe. Oh, okay. So.
Oh, okay. I think I see. So you're saying that maybe I can take a POVM that's not covariant,
Yes.
and then I dilate it, and I have a
then it
covariant
becomes,
one. I don't think this can happen, but I don't know any theorems about
that
this.
is what I asked. That if this is
Uh-huh.
if and only if kind of thing, like in both senses, like
I don't know.
from sharp you.
I know that there is a dilation procedure that works, and I know it can be made to preserve covariance.
Okay.
And that sharp POVMs are unique
Right.
given the representation. There are it's interesting. So when you that was my experience as well. That when I start learning about these things, then there are obvious questions that you ask, and then no one knows because they turn out to be difficult or just not yet studied. So it's gonna happen again that I will just say I don't know, just to make sure. We go. Okay, so now when I know what are quantum reference frames, I will tell you how I think we should deal with describing other systems with respect to chosen frames. So when I have a frame and another system, so I assume that on the system the same group acts as well. The available operators need to respect the choice of the frame. So there will be operators on the composite system, and the effects that the operators that I have access to I have to be able to construct them from whatever I want on the system, and only the frame effects on the frame. So this is to make sure this is the subset. So I take the span and the closure. So this is also a Banach space. So it's a subspace of the Banach space of all bounded operators on the composite system that can be constructed with a given frame. Another way to put it is the POVMs that will have that effects living in this subspace. They can be seen as measuring the frame observable and also something else at the system at the same time. As like, so the probabilities will be probability distributions will be how is this called? Marginals of each other. So this sort of effects in this space are called framed, ER framed. This is quite important, and it took some time to realize that this is an important notion, and now I think it's just crucial. This sort of space, and there are different ways to speak about this. You can take this span, but you can also think about it differently. I'm gonna probably talk about this next time. But conceptually, this is just acknowledging the fact that I have decided what my POVM of the frame is, and then I stick to it. I don't allow myself to use any effects that I cannot actually use.
That is unique. I mean, which is like covariant and also sharp. So do you want this EX to be sharp here?
No. So now I have any frame. So I have a covariant POVM, and so I fix this, and I also take a system, and I restrict. So normally I would say, okay, operators on the composite system are just operators on the composite system.
Right.
But now since I've chosen a specific POVM, so now covariance doesn't play a role yet, but I've chosen a POVM.
Right.
And then I restrict to make justice to this choice.
Okay. So you have fixed the POVM on the reference system.
Yes.
And now whatever you can do with the whole thing.
Yes.
That is the,
Yes.
okay.
So any observable on the composite system that has the effects that are not in this subspace, I don't consider it physical, because I cannot access it with the chosen instrument. But we also have this other property, this other condition, that there's operationally meaningful effects, they should be invariant on the composite system. So this G upper script is to say that the operators that are in here, they are not, they're invariant with respect to the group action. So now the group action is on the, because the group acts on the system, on the frame and on the system, I have this so-called diagonal action, so I can act with the same group element on both systems at once. And then the physically meaningful, operationally meaningful observables, I require them to be invariant. So now I want to intersect these two properties. I want to require both invariance and this framing. So I define this intersection. And so my physical things, they should have, my physically available effects, they should live in this intersection. But then the question comes if this is even possible to satisfy these two properties at once. It's totally unclear to me as when you first see this. But there is a positive answer to this question, and this is given by the relativization map. So it happens that, well, there is a procedure. You have a question? No.
Can you just go to previous slide?
Yes.
I need to see.
So this is the O subset. So I put more restrictions on my set of available operators here, because yeah, I have some principles that I want to obey. And now it turns out that I can construct elements of this space. It is not empty, and I can construct them by means of the relativization map. So in fact, for any operator on the system, I can construct a corresponding operator on the composite system that satisfies both these properties. It is invariant and it is framed. And it's given by this sort of integral, which Leon gave meaning to some 10 years ago. So when you just see it, it doesn't make sense. I mean, what does it mean to integrate with respect to a positive operator value measure? So this is unclear, but in fact you can make sense of it. So this is just a symbolic notation, but it does what it does. So you can make manipulation with these things as this was just a measure. And then you can see that when you multiply, when you act diagonally and you change variables, the fact that ER was covariant, it allows you to prove invariance of the outcome operator. I will tell you how this integral and actually more general integrals will be defined next week. But for now, well, just believe me that there is such a map, and it's a very nice map. So it's a quantum channel. It's positive. It preserves effects, and it's completely positive and normal and whatever you want. It's a very well defined, well behaved procedure. I will let you stare at the yen. So this is yen, yen map. It's the yen map because it was developed as a generalization of the dollar map. So I don't know what's next.
Euro.
Euro map, yeah, maybe. And so obviously this depends on the choice of the reference and on the reference frame observable. So therefore there is this upper script here. So this map is understood as incorporating the reference explicitly into the description of S. So in non-relational approach to quantum mechanics, we only just care about the algebra of the system. But now I'm saying that we should actually care about these observables that are defined in the composite system, that they are invariant, they are framed, and this is a procedure that maps this standard description to the other. and we define the notion of relative observables as being in the image of this map. And we take the closure because it's useful. So the relative operators, this is a Banach subspace weakly closed of the algebra of bound operators on the composite system. And these are those operators that satisfies the properties and can be accessed via the specified reference frame. Okay, questions? This is sort of crucial. So this is the definition of relative observables, and then yes.
Okay, so now this is, of course, a subset of BHS, like the.
No, this is a subset of the B of the composite system.
Okay, this.
Yeah,
so
because
this
the
not
map
only for the system, but also for the joint system.
So as a result of this, taking this integral, you have an operator on the composite system.
Okay.
Yeah. So Yen can be seen as a channel from the system to the composite system, and the image of this channel is in the invariant algebra, and it's also in the framed subspace. So in the intersection of these two things that we wanted. Yeah, this is beautiful when you think about it. It's incredible that this can be done. I think. So this is how we define relative observables, and then the relative states are the corresponding quotient state space. So we define, since these are the only observables that we have access to because they're framed and invariant, we should identify states on the composite system that cannot be distinguished by them. We take the operational quotient.
Right.
And this is the definition of a relative state that we take. So we can see this seems very different to what people usually do, because they just say, okay, this is a state and this is relative to this system, and then the other state will be. So the state of the relative state is usually just the state of the system. And here it is a class of states on the composite system. So apparently a very different thing. But it turns out that this perspective, they're not incompatible, because the Yen map is normal. It has the predual map. It's normal and positive and blah blah, it's a channel. It has a predual map that then will take states on the composite system to states on the system alone, because it goes the other direction, if you remember. A map goes from the system to system plus frame, and the predual goes from the states of the system plus frame to the states of the system. And in fact, we have this is a state space, this total convex blah blah quotient operational state space, but there is a bijection between states of the system and these classes, which is given by this predual map. So it's the same thing. To specify a class in here as to specify what happens to an element of this class under the predual map. I can try to write down something if you want, but maybe it's clear enough.
For me, it's good to write actually.
Okay. Nice. So this is non-trivial and maybe surprising. Later on with the frame changes, we will use this second perspective on the relative states. So not as classes on the composite, but just states on the system, and we will map one. Yeah. This will come. What else I want to say is that so this quotient state space, this is total convex by construction, but the image of the predual map in the states, this is no longer a total convex state space in the sense that we described. So there is a bijection But well, it seems that this quotient space is like a more reasonable notion, but it is possible and in fact useful to think about relative states also as just some states on the system. And you can see this is going to be a subset, and as we will shortly see, this can be the case. So if the frame is good, if it's nice, if it's good enough, then we can this subset will be big. So many states will be accessible with the frame. But if the frame is not very good, it's not very precise, then it turns out that not all the states of the system can be relative states. Okay, so this is the subject of what's coming. So how we get back, if it's true or not wrong, what I'm saying, that what we measure are actually these invariant and framed observables, and how come we can use quantum mechanics as we do and not get into troubles. So the way it works, I think, is so first I need to say what is this restriction map. So for any state of the frame, I can define the following procedure. So if I have this sort of effect, so I have one effect on the frame and the other on the system, I can apply my state of the frame to the effect on the frame, and then do nothing to the other effect. So this is very simple, and it turns out you can extend this procedure to by linearity and continuity to the whole space of effects, or even like bounded operators and whatever you want. Another way to see this thing is that the image of an operator on the composite system, when evaluated on the state of the system, is the same as I would just take the original operator and evaluate it on the product state. Does that make sense? It's the restriction. So it's also a channel, actually more than that, but it's not gonna be important. Now it's a map from the composite system to the system itself, and it's understood as so when I know what's the state of my reference, I can externalize it again. I can sort of forget it. In my description that is given on the composite system with my relative observables can be conditioned upon the choice of the frame state. So now comes the trick. So if the frame is localizable, I can do the following. I can take an effect on the system. I can relativize it so that I consider it as a physical thing, but then I will restrict it because I know that my actual reference frame is prepared in this localized state, and then it turns out that nothing happens to my observable. The understanding of this is that it makes no difference if I just do quantum mechanics as I used to, or I do relational quantum mechanics with localized frames. So we can check that it works, and maybe it's instructive. So we need to take this limit because blah blah. This is the n thing, so this thing is framed and invariant. And now if you apply the gamma map, the restriction map, it only acts on this first factor. And well, if you apply this sort of effect to a state, as a result you get the measure. And since we assume the frame is localizable, this measure is gonna be arbitrarily close to the delta measure, and if you take the limit, it's localized at identity, it does nothing. So this is one thing you can prove that works, and try to understand it in terms of externalizing the frame again by knowing that it is actually a localized system. And more things are true in the case of localizable frames. One is that these relative states, understood as subset of the system states, are dense, so you can get anywhere as close as you want to any state in terms of relative states. And this algebra of relative operators, it is indeed an algebra because in general It doesn't have to be. It's just a Banach space, but it is an algebra and it's isomorphic as a von Neumann algebra to the original algebra. So the upshot is that the relative description is indistinguishable to the non-relative one when the frame is localizable. All right. So this is conceptually important, and the last thing, probably for today, are the frame transformations. And it goes as follows. So the setup is so-called internal frames. So because we could think about something else, we could think that okay, I have a system here, and I can choose this frame or this other frame to describe the system. But this is not what we're doing here. This is current work. But in all other frameworks that I'm aware of, what is being considered is the internal setup. So you start with a big Hilbert space, and then you identify some subsystems of this big system, and you treat them as reference frames, and you're interested in how the relative description of all the rest of the system will change when you change your systems, your frames. So for us, the setup will be that we have this big Hilbert space, and it is decomposed with the tensor product with two different things. So one is going to be the first frame, second frame, and well, of course, the representation of the group is going to decompose accordingly. And if we want one first and second system to behave as frames, then we need to choose the frame observables. So that's the starting point. And I say that we have a pair of internal frames. And now there is this specific set of operators that I will consider. So these are, well, actually there should be like a convex hull and a closure. Sorry, I forgot this. So I take these things and I generate a convex hull. So what the things that I take is that I take any effect of the second frame and anything I want on the system. So this lives on H2 and S, and I relativize it, and as a result I get something that is invariant on the global level and also framed with respect to the first frame observable, to the first frame. These are relativized effects of this form. And I consider some. It's complicated. Yes.
Can you go back to the definition of the EL map?
Of course. Yes, here.
Okay. What does it mean when you have this map with respect to the reference 1, and then you are having this on the
for A here, so this is the R1, and for A I just take something I want on the composite system, because now the system is like everything except my frame. So now from the perspective of the first frame, the system is the second frame plus the system.
Yes.
If that makes sense. So, well, this is something I can consider, and I would be interested in the corresponding state space. So I again take the quotient, and it turns out that it's the same thing as I would consider the relative to the first frame states on the second system frame and the system. So I use the second formalization of the relative states, and then I take a quotient with respect, another quotient with respect to the second framing, because I only allow this sort of effects here. And it may seem arbitrary, but maybe next time when but it just works. So let's put it this way for now. So when the first frame is localizable, or maybe I will actually try to explain this. So if the first frame is localizable, this sort of effects that I will get by relativizing these things, they will be invariant and they will be framed with respect to the first frame and the second frame. And if the frame one is localizable, this way I will get to all of such effects. So the setup here, when I've chosen my two frame observables, I consider bounded operators on the whole thing, and they have to be E1 framed, E2 framed, and also invariant. And if the first frame is localizable, by doing this, I can get to all this, this whole space. And this is the the universe of discourse of this setup. So nothing happens outside. I'm not interested in things that are not aligned with my choices. And it turns out that when I do this sort of choice, then I can define a frame change transformation. I take as an input, I take states that are relative to the first frame, but also framed with respect to the second one, and as an output, I get the same thing reversed, and I can define this map, and I can show that, well, it is indeed well defined. So it's defined on the equivalence classes, and to see that this is the case, so why I need to take this E2 framing here is because, as a result, I will take the relative states with respect to the second frame, and they are necessarily only, they cannot be distinguished with Jesus, it's so difficult to say this, because I take this pre-dual thing and the relative operators are framed. The result of this thing is not going to depend on it's not going to distinguish the states better than with the framing of the second frame. Okay, this is maybe not super clear, but the fact is that when you restrict to the setup, this map, so what it does, it's also like very much inspired by other works. So what it does first, I take the state on in here, I attach sort of externally a localized state on the first frame, and then I apply the pre-dual of the second map to get into the relative states, and I take the limit in the end. And so this is a wild construction, so it's totally unclear if this makes sense, but it does. It's well defined, and moreover it makes this diagram commute. What the diagram does is that, so imagine I have a state on this big system in the invariant on the invariant subalgebra, and I can be interested in the corresponding relative state with respect to the first frame, but I also take care this is a projection, the quotient projection with respect to the second frame, and I can do the same thing on the other side, and this map makes the whole thing commute. So the transformation is compatible with the existence of an auxiliary state on the total thing. So I would say it makes sense. And then if the second frame is also localizable, then this map is invertible. I can go back with an analogously defined procedure, and it's also composable in the sense that, so I need to take this, so I have now 3 frames. The third frame doesn't have to be localizable, but if the second one and the first one, they are, then this map stays defined, and I can compose them. And it turns out that I get exactly what I would just do if I was transforming from the first to the third frame, but I also need to make sure that I take this quotient, because this map here, it doesn't know about the second frame, so it's not gonna work. But I need to take the quotient, and then everything is fine. And the last thing I want to say is that this procedure, although coming from very different ideas and using very different tools, it is in agreement with other transformations defined before. So the V here is a specific formula defined in the perspective neutral framework for an analogous setup. But then this is a unitary map. So to act with this on states, I need to take it on two sides. And then if I do this, I don't get the same thing as I would with my channel. because as a result of my channel, I don't get a state, I get a class of states. But if I take care of this, so I also take the relevant quotient, these procedures, they're indistinguishable. So if you accept that these choices of frame observables, they have to be acknowledged from the very beginning, you can indeed define invertible and composable frame transformations that are, and if you accept this setup, then what we're doing is in agreement to what other people are doing on the domain of common applicability. So this was only checked in the simple case for, like, you take a finite group and then you do what they do and you do what we do, and these things are indistinguishable up to the equivalence relations that we require. Okay, it's exactly 6. Do you have any questions? I know it was quick, so this is all. So we were actually, so it's in my thesis, but it's also in a preprint on archive, and we're in a few days we're gonna put up like another version of this preprint, and probably like the almost final one. So if you want to read about it in detail, then you're most welcome to do so, and I'm very happy to answer questions and help you understand, and maybe you will also help me understand, because sometimes it just, you find out what theorem you can prove and then you prove it, but it doesn't necessarily mean that you understand it. Okay, so this is it. I'm done for today. Again, any thoughts or questions, confusions?
Could you just go back to the,
Of course.
because the last so these things.
Yeah, I think I didn't tell you what's this G here. But so the idea is that I'm only interested in the operators on the whole thing that are invariant, the whole thing, and then this is the corresponding quotients by state space. So But you had another question, probably.
Yes.
Sorry.
No, I'm just trying to somehow. Okay, so this is now H. So this S H2 tensor HS.
Yes.
E2 framed and
R1 relative.
So this is a subset of the states in HS.
No. So this omega is a state on this system, on the composite system.
Okay.
The second frame and the system, but it is an image of the predual map with respect to the first frame. So it is a relative state, this thing. But then on top of this, I take a quotient with respect to the framing on this factor. So I will identify relative states relative to the first frame understood as states in this composite system if they cannot be distinguished by the second framed observables.
So it is not only the system state, so as to say.
It's a class of those.
Yeah.
It's a class of such states. And not any states, but the relative states. But to make this well defined, this R1 is assumed localizable. So in fact, I can take any state on the composite system as my relative state, and then I take a quotient to make sure that the choice of the second frame observable is acknowledged. And then I do exactly the same thing on the other side.
Okay, so these are states on this tensor. I mean H2 tensor HS, but now I choose them in such a way that E2, like for the second system, this two reference frame, this POVMs cannot distinguish.
Yes, so I do what I do. So I take an operational equivalence.
Erasing the information of the second system somehow.
In a way, yes, yeah. And this has to be, so why this map is well defined on these classes is because I take this predual of the n here which is defined with respect to this second frame POVM, and so I didn't give you the details, but because the relative observables, so the observables in the image of the second frame, they are framed with respect to the second frame observable. So they're not going to distinguish states that are like better.
Right.
So I can take this equivalence relation here, and this map is still well defined. And I'm not forced to do so. So this map could be defined without these classes. But then if I want invertibility, I need to do this on both sides. Yeah, it's quite complicated, but it is what it is. So I think actually the setup of this operational setup is more suited for sort of external frame changes, so that you consider a system from one perspective and the same system from another perspective, and how to map between the two. So we're gonna speak about this next time. So this is so now I finish with the work that's out there, and next time it's gonna be more speculative. So no theorems have been proven yet, but they seem to be there. All right. Thanks a lot. I will stop the recording.